started. I'll hate myself tomorrow if I forget that part, because that means I'll have to redo it. So big picture, this unit we're talking about how to include effects of predictors that require more than one slope to describe their relationship with an outcome. So the first example that we had of that was predictors that are categorical, that have more than 2 categories, so 3, 4 category predictors. And the solution to that was to create new predictor variables that have number of groups minus 1 new predictor variables that are coded 0 or 1, so that we can differentiate each group relative to a reference group. And we did that. And then the second one we did last time, which was like 10 days ago, it feels like about 2 years ago. It's like, anyone else feel like just like a fish out of water? Like, what am I doing? Who am I? What am I talking about today? Oh yeah, I work here. Oh yeah. The other one we did last time, quadratic effects. So the idea of a continuous predictor that needs a nonlinear slope as opposed to linear. And we looked at an example relating income to age, which has this lovely quadratic function. So the slope is positive. The older you are, the more money you make at the younger end of the distribution, but at some point that shuts off and switches directions. And we looked at that. And then the next one that we're ready to do then is something what is known as piecewise slopes. So any questions or things that you want to review before we jump into something new? So the new part lies in creating a distinct type of predictor variable to capture a nonlinear relationship with a series of linear relationships. That's what's new. But the process is pretty much the same as what we've had. So let me get that thing started. All right, I'm sharing, right? Everyone can hear me, see me? Good? Okay. So this is a plot that shows the predicted, or not predicted, let's put it this way. This is the mean annual income for each distinct year of education in this data set. So I computed what the mean is for income for each possible year of education here on the x-axis, and I made a picture. So that's the black line, and then standard error confidence intervals around that with the red line here. So previously, we had used education as a predictor to demonstrate just putting it in as a regular predictor with a linear relationship. And that doesn't make a lot of sense for a variable like education, because education, even though it's quantitative, is conceptually, it's both kinds of people and amounts of education. Because getting a high school degree, for instance, opens doors relative to only having 11 years of education. So there's a big jump, for instance, in potential income right here. Likewise, hopefully getting advanced degrees opens doors for you. So it's not just having one more year of education, it's getting to the next level with respect to the degree that you can put behind your name. So to try and get at this idea of a different effect of more education at different points of education, I'm going to fit what I call a piecewise slopes model. So this is also known as linear splines. And in this type of model, what we're going to do is take this quantitative predictor on the x-axis here and carve it up into sections. And we're going to fit a separate slope through each of the sections. So just based on the picture and based on what I know about years of education within the US system, I am hypothesizing that for people who are at 11th grade or below, that there's basically no effect of having more education. If you finish 7th grade versus 8th grade versus 9th grade, that's really not going to help you get a better job. That's my hypothesis here. There is likely to be an effect of graduating high school. So there is sort of this bump that you can even just see in the data, transitioning from 11 years to 12 years. And then I expect that having more education should hopefully be related to more income after that. So this would be like post-college, master's, PhD, that kind of stuff out here. So I'm going to take this predictor, carve it up into 3 separate sections, and fit a linear slope for each section. Okay, does this make sense as a concept? So it's a way to create a nonlinear pattern by sections of patterns that are each linear. The trick is how to get the predictor variables to be set up to do this correctly. So what I'm going to do is create 3 new predictors. The first one is going to capture the change in income as a function of 1 year more education for people who did not graduate high school. The second predictor, the second column here, is going to capture the change in income for graduating high school relative to somebody who is in the 11th grade as a model reference for the intercept here. And the third predictor is going to capture the effect of more education in people who have at least a high school degree. Question?
So how do you know where you divide?
Question was, how do I know where to divide? There's two choices here. One is you make the call based on your understanding of the variable, the theory you're working with, conventions with respect to, like a lot of quantitative variables have cut points like, oh, if you score above 15, that means this or something. So if you have a variable that has points that are sort of recognized as transitions, you can use those. If you don't, and you suspect that you have sort of these nonlinear relationships, you can ask the model to find where to cut it. That is an advanced topic that I don't have an example for, but the term for that is a latent knot. So latent means unobserved, where one of the parameters that you have to estimate is where to split it, basically. That makes it a nonlinear model rather than a linear model because you have to estimate the knot, and so it's a little trickier to do in software, but it is certainly possible. So this works for variables where you can either, based on what the data look like or based on what your theory says or some combination, you know where to cut it up, these sorts of slopes. So I once had someone ask me, what if you wanted to do like years of age in adolescence and you wanted to do like before puberty and after puberty? Could you do that? You could, so long as you have a variable in your data set that says for each child exactly when puberty happened. Like what age were you when that happened to you? Because you'd have to have that in order to know where to put the person with respect to these predictor variables. So this does presuppose that you know where you want to break up the lines. So in terms of the coding scheme, the yellow here is going to be my intercept. So that's why I have it, this zeroed out here, basically. So the model intercept is going to describe income for somebody who has an 11th grade education. I have a question here on the graph. Why do we need the 11 to 12 line instead of just before grad and after grad? So I decided to create 3 different pieces of this instead of 2, because to me it looked like this is a qualitative shift in basically going from 2 to 11 and then a big jump in going from 11 to 12. But that's actually an empirical question as to whether this should be just before and after high school or whether I need all 3. So one of the things that we'll do in the data analysis is test whether or not you only need 1 slope or 2 slopes or 3 slopes, because we can ask for the differences between the slopes and get a hypothesis test as to whether that difference is different than 0. All right, so I am setting grade 11 as my reference. That means that all the predictor variables are going to be zeroed out at grade 11, and the model fixed intercept is going to tell me the expected annual income for somebody who finished 11th grade. So relative to that as a 0, 10th grade is 1 less than 11th. So with this defined as what 0 means, I have to go negative. 9th grade is 2 less than 11th. And if I had 8th grade in here, what would I have the value be? -3, exactly. So you're defining what 0 means, and everything is relative to that. So this variable would be coded, you know, -6, -5, -4, -3, and so forth. So it is going to indicate the effect of one more year up until 11. But then watch what happens after 11. It shuts off. So according to this variable, there's no distinction to be made from 11 onward. That's because those distinctions are going to be picked up by the other variables instead. So likewise, the other two variables are zeroed out up until 11 because they are not applicable yet. They haven't been turned on yet, so to speak. So the second one is going to capture the acute change from 11 to 12 only, and then shut off where it left off. So it stays at 1 because that was the highest value. And if I had like another one, if I wanted to do 0, 1, 2, these would all stay 2. So there's no more change being indexed by this column after 12. It's done. Then the last variable picks up where the second one left off. So after 12, grade 13 is 1 more year than 12. Grade 14 is 2 more years than 12. So it's going to indicate the effect of 1 more year of education specifically within people who at least finished high school. So the first column operates for this section of the curve only. The second column takes the middle part, and the third column takes this part. Okay, question?
So keeping that 1 as yes,
Mm-hmm.
I didn't understand why. I mean, isn't it supposed to be like -1 or something like that, because those grades are going up and you want to keep it at 12?
I want to keep it at 12, and because 12 is coded 1,
So
then
because it's multiplied by 1, is that
it's not multiplied. It's just like, basically it's like, do you want to keep track? Do you want this variable to keep track of more education past 12? And the answer is no. So I'm lumping together, like if this variable was all that we had in the model, this would be, did you graduate high school, yes or no? Like that's what it is. So we're lumping together the 12s, 13s, 14s, and everything.
as 12?
As 12, yeah. This variable by itself only splits high school and not, but when you pair it with the other two, it separates out before high school effect and then after high school effect. So they all work together to do this carving. Okay. So here's what we found, and then I'll show you how to make the program figure this stuff out for us. So the model looks like this. I have 3 slopes. So beta 0 is my fixed intercept. Beta 1 is the slope for a 1-unit increase in education up to 11th grade. Beta 2 kicks in after that and shows me the change in predicted income from 11th to 12th grade. And then beta 3 kicks in after that and gives me the further change in income after 12th grade. So all of these are in the same metric of 1 more year of education. They just cover the range at different points of the variable. And then E, because the model's not perfect. So if this model is useful, what we would see is that the variability of the E's, and what is that called again? We'll do a little vocabulary review here. The variability of the E's is called what? Error works, but there's a name for it because there's a value in your output that you're going to be looking for. Yeah, residual variance. Yep. So I call this E residual. You can think of it as error. Other words, discrepancy, offness, all the reasons why people make different amounts of money that have nothing to do with education, that's all still in here. So if this model is useful, should the residual variance go up relative to a model with no slopes or down? So if I start with a model without these slopes and I get my E variance, And then I fit this model and I compare the E-variance. Should it go up or down? It should go down. So the original empty model has all of the variance in the outcome. There should be less residual variance after these slopes have their say. So here's my summary of what happened. So F is my new test statistic. F is used anytime that you are testing more than one slope at the same time. Inside the parentheses, what are these numbers right here? Degrees of freedom. Yep, and the 3 is called numerator, and the 730 is called denominator. Why is this 3? What does 3 refer to? Yep, number of slopes. Yep. And the 730? Yeah, number of slopes that I could have had. Where that comes from is sample size minus number of fixed effects. There are 734 people in this analysis. I have 4 fixed effects. I've got 3 slopes and an intercept. So that leaves me with 730 as the number of slopes I still could have added.
It counts the beta 0.
It counts the beta 0. Yep. So my F test statistic is 47. That number shouldn't mean anything to you. It is a ratio, basically. So F is a ratio of information that your model predicted per slope divided by information left over per slope you could have added. So you want your F to be greater than 1, because 1 would mean that your predictors did about as well as chance. This thing right here that's next, MSE, what does that stand for? Good guess, but no, not standard error. Yeah, mean squared error. That's what it's called in your output if you are using SAS. It is called mean square residual, I think, if you're using Stata. Those are synonyms. But what does it mean? 159 is what? This is my residual variance. So if I take each person's E value, I square it, I sum across people, and divide by the 730 slopes I could have had, that number would be 159. So this tells you the amount of variability in your outcome variable that has yet to be explained. This p-value corresponds to the F. This will show up in your output as well. So it is unlikely, it would happen less than 0.01% of the time that we would see an F this big, meaning that it is unlikely if these 3 slopes were actually 0 that we would have found what we found. So my model is significant, is the way that I would interpret this. The collection of slopes work together to significantly predict annual income as my outcome variable. But how good is it? That's next. Our friend R square. And the unsquared version of just R here next to it. What's R square tell us? An effect. It is an effect size. Yep. There's 2 definitions of it. Let's do the proportion one first. How much the model explains. Yep, it's the proportion of variance that was explained by the model. Said differently, 16% is by how much the residual variance was reduced relative to a model without any slopes in it. So we've got 16% of the total variability by these 3 slopes. What's the highest R square can be? Not a trick. 1. Yeah, what's the lowest it can be? 0, because it's squared, yes. So F is in a squared metric, R squared is in a squared metric, MSE is in a squared metric. So I say that because if you're looking at these numbers and thinking, okay, if it's negative, it means this, it's never going to be negative. They're always going to be positive. So R square is the proportion reduction in variance relative to the empty model. This model got 16% of it. MSE is how much is left. And then if I unsquare that R, I get a correlation. What is it the correlation of? The other definition of R square. What is this the correlation between? If I want to think about this result as describing a correlation. I'll give you one of the variables, it's y. The original outcome variable in your data set that you're trying to predict, that's one of the two variables.
And the overall slopes?
Has to do with the slopes, but it's not the correlation with education, though, because that would be a linear model. Education has 3 slopes, but it's related. Observed and predicted, yeah, the predicted part is y hat. So if I computed for each person what their predicted income is supposed to be for this model based on their education, this correlation R here is the correlation between what y is and what the model said it should be. It's y with y hat. So it's not the correlation of education, because education would have only one slope in that case, and I've got 3. Okay. So this model statement here is sort of a global summary of what happened. It describes how education, according to this model with 3 slopes in it, predicts income. Generally speaking, it does so significantly, and it does so with the correlation of 0.4. Now we can drill down into the parameter estimates, so the actual values of the intercepts and slopes found from the data, and talk about what happened specifically to each section of education. So beta 0. What's that thing? We'll do definitions first. What's beta 0? Intercept, yeah. And the definition of an intercept is what? What y is when x is 0, yep. So in this context, y is income, and when x is 0 is when all 3 of these new predictors are zeroed out, and that happens for somebody with 11 years. So yes, this is the predicted income for somebody who has 11 years of education. That person is expected to make about $8,500. So that's my model reference point. So I can talk about what happens as we move backwards from 11th grade, or I can talk about what happens as we move forwards from 11th grade. We'll go backwards first. Beta 1 is the slope of less than high school. So this variable tracks the change in education from whatever the sample minimum is, I think 2, up to 11. So the slope estimate for beta 1 is negative 0.27. Negative slope means as education goes up, what happens to income? Goes down. That's kind of surprising. You would think that more education is related to more income, but the data say nope. However, the standard error for that estimate is 0.6. So the expected difference between the sample slope and the population slope on average, that difference is 0.6. So if I take estimate divided by standard error, that creates my t-test statistic, which is 0.65. And relative to a t distribution, I would see a result this extreme or more extreme like 65% of the time. That's my p-value right here. In other words, if the true slope in the population were 0, I could get a slope this big like 65% of the time, just from normal sampling fluctuation. So it's negative, but it's non-significantly negative. And the last piece of this here, this is what's known as a partial correlation. It's an effect size. So it's a way to put the strength of this effect into a metric that people readily understand, because R ranges from -1 to +1. So it's a very, very tiny correlation. In other words, income basically has nothing to do with education from 2nd grade to 11th grade in this sample, just like the picture says. Okay, with me so far? Now, high school degree, that's covered by beta 2. So relative to 11th grade, the slope describing the jump in income that you get in if you have 12th grade is 4.68. So people who graduate high school make about $4,600 more in this sample than people who don't. So relative to 11th grade. Standard error is 1.88. Estimate over standard error gives me my t. So this t is significant. It means that the slope is over 2 standard errors away from the null hypothesis of 0. So I would see a slope this big if the true slope were 0, like 1.3% of the time. So that falls in unexpected territory, significantly positive slope. Effect size for it, 0.09. So still a very small effect, relatively speaking. Last but not least, from 12th grade on, now beta 3 kicks in to talk about what happens to those people. So the slope for the the change in income per additional year of education after 12th grade is 2.12. So $2,000 more per year after 12th grade. Standard error is 0.2, so that t is 10, meaning that this t is 10 standard errors. This slope is 10 standard errors away from the null hypothesis of 0. Very unlikely to be that it came from a population with a slope of 0. And a fairly large effect size, so a correlation of 0.3. So the story then changes a little bit as a function of these more specific results. So if I just ask you a blanket statement, is education related to income? You can't say yes or no. It depends. If you don't have a high school degree, no, education does not predict income. If you have a high school degree, yes. If you have more than a high school degree, yes. So putting those slopes on the picture, this one looks okay. So it actually does look like a negative slope. This one looks okay. Now, just eyeballing these pictures, what do you think of the fit of the model predicted income that's given by these straight lines right here to the actual data that's given by the solid lines? Does this look like it does a good job capturing this trend with a line? Ish. This part the line over predicts, this part the line under, yeah. This under and this one over. Yeah, it could be, suggestion could be quadratic, yeah. So this is still within each section a linear model. This to me looks like it could be bendy. So I actually did try that, and quadratic doesn't help fit much better. What I think would be required is actually more pieces. because there's a big jump when you go from 15 to 16, which would be getting a bachelor's degree. Not much of a jump if you go from 16 to 17, and another jump from 17 to 18, which presumably would be like a master's degree. So it looks like we need more pieces in this last section. So you could fit curvilinear effects, you could fit additional pieces, there's various ways to go about it, but this would be, to me, what it looks like we need here. Okay, how are we doing?
So you decide to make these distinctions after you already tried getting this slope?
Yeah, I think so long as you're honest. So looking at this and then sort of post hoc saying, yeah, this didn't fit, let's try something else, as long as you describe that and you didn't like pretend that you knew what it was supposed to be all along, I think that's where you want the reader to have access to the same information that you did to make your decisions and to describe your process. Yeah. Do you want to see how to make the software do this for us?
Elisa, I have a question.
Hit me.
So why did you decide to use less than 11 as a predictor instead of an intercept here?
Why did I put the intercept at 11? Is that the question?
Why did you use it as a predictor instead of B0? Instead of it being like the intercept?
I'm sorry, I'm not understanding the question.
Why did you use less than 11 as a predictor instead of making it like an empty model, for instance?
So is your question then, do we need this slope?
Correct.
Is that your question? Yeah. The data say no. Yeah, so the data say basically this column isn't helping us predict income. Keeping track of just how low your education is if you didn't finish high school isn't helping. So yeah, it kind of looks like this line for the less than high school folks could be flat, meaning that we take this variable out of the model and we only need these two. So what it would do is change the reference for the model from, right now it's 11, it would be basically everybody from 2 to 11 would be lumped together into the same category. So I could do that. But if I wanted to make a point that more education doesn't help for people who didn't graduate high school, then I would leave the slope in so that I could make that point. More generally, in refining your models, it's almost never the case that you're going to fit a model, write it up, and turn it in, and that's the only thing you fit. It's always kind of an iterative process. Whether or not to leave in non-significant results depends on whether that result is part of your question. So like if you have a question about how, this variable predicts this outcome and the answer is it doesn't, leaving it in the model to make that point may be necessary. If your question is like, let's just see what predicts this outcome out of these lists of things, then taking it out of the model would make more sense because it didn't have any special status. So I can't say that there's like a general strategy that always holds, it depends, but non-significant results I think are important if that is the answer to the question. Other questions? So you'll get a chance to practice doing this in one of your homeworks. So I wanted to show you how I made SAS and Stata do my bidding. Come on, there we go. So I've got example 3 here on page 10 to show you. Make this a little bit bigger. So the trick is creating functions rather than assigning specific values for every possible level of education. You could write code that says, if education equals 9, then make this one -2, make this one 0, make this one 0. If education equals 10, make this one -1, make this one 0, make this one 0. But that would be very inefficient and potentially take a lot of lines if you have a lot of distinct values. So we're going to use functions that do the same thing with less code. Right. So here's the objective. And in general, whenever I fit these models in real life, I make this table first. So this is not just pedagogy, like this is me writing out what the code is going to do so that I can like see the logic and execute the logic in the code. Where would you use these models in life beyond just this class? Longitudinal data. So multiple baseline intervention designs, where you have, say, several observations during a baseline period, then you do something, and you want to see if the outcome changes as a function of whatever you're doing, and then maybe you take it away. When you have different sections of time, these types of models are very useful for directly addressing whether change is happening when it's supposed to, during as a function of what you're doing for your intervention. These models are also useful for if and how much types of variables. So if you have a predictor where a lot of people have like a 0, like it doesn't apply to them, and then there's people who vary in amount, these sorts of models can help you separate like what is the effect of having this versus not as one predictor, and then how much if you do. So these two columns right here look like that in theory. This column is like, do you have a high school degree, yes or no? And if you do, how much more education do you have? There's a lot of variables that lend themselves to that kind of partitioning. For instance, if you have something like substance abuse, let's say you give out a scale measuring substance abuse, you may have a lot of people who have 0s, meaning they didn't say that they have any history of those problems. So you might make one variable that's like, do you have a history of substance abuse, yes or no? And then for the people who do, how severe of a history is it as a separate predictor? So that way you can classify sort of kinds as well as amounts. So I think these models are kind of underrated. That's why I want to give them to you as part of your collection here, because I think that they could be used in a lot more places than they are.
What is that model called?
I call this either piecewise slopes or linear splines. But for today, we're carving education up as follows. Let me see if I can almost fit it all on one page. Linear splines, it's S-P-L-I-N-E-S. A spline function, means like it has knots. A knot is the point where the splines join. So where the slope shuts off for one and starts up for another is called a knot point. And the splines connected. Kind of like Tinker Toys. Do you remember Tinker Toys? Like they're like little sticks, and there's like a little wheel that you shove the sticks into. Like the wheel is the knot, and then the sticks are the splines. Okay. So step 1, make 3 new empty variables. So in SAS, it looks like this. New variable name equals dot, means missing, and then a semicolon. So this is like 3 separate statements on one line of code right here. In Stata, it looks pretty much the same except for the word gen in front, with the command is generate. It's the analog to compute in SPSS syntax. And in R, the missing data is the letters NA instead of a dot. But it's the same with the semicolon because I have multiple commands on one line. Then I have 2 possibilities here. So if education is LT, can you guess what LT might stand for? Less than, yeah. And can you guess what GE might stand for? Greater than would be GT. Greater than or equal, yeah. So otherwise you would leave out the people who have a 12, because the first command is less than 12, and this one will be greater than 12, and you wouldn't have 12 as one of the conditions. So this is less than 12 and then greater than or equal to 12 is the two conditions. So this part in SAS is setting up the conditionality. So in a given row, if the current variable for education is less than 12, then do the following. And note all the semicolons. Then do semicolon, make the variable for less than high school, make the variable for graduating high school, make the variable for over high school, semicolons after each of these, and then an end goes with this do. So it's like a sandwich. Do this, do this, do this, do this, end. So end then shuts off the conditionality. So if we have less than high school, or less than 12, excuse me, then less than high school is the original variable for education. So what the column on the left-hand side here, minus 11. So I'm not writing out a separate statement for every possible value. I'm using this function. So education minus 11 computes the part that's in the green box here. The other ones, now we're filling in the rest of the columns with zeros. Because for somebody with less than high school, these columns are not relevant. They're not going to help predict their score, so they're zeroed out. Okay, with me so far? Questions? All right. Then the other case, if it's greater than or equal to 12, first column, zeroed out. So less than high school goes to 0. Second column is a constant. One to out. Is that a phrase? If you can zero something out, can't you one it out? I just did. One it out. Then last but not least, the third predictor is another function. It's education minus 12. Because 12 is where we need this slope to start from. So 11 to 12 is covered by the second predictor. 12 on up is going to be covered by the third. That's why it's 12 here. So I can do this in 2 statements in SAS because I'm allowed to group commands together if they all meet the same condition. Stata, I tried to do it in Stata and I could never get it in any way that looked right, so I write them out. So these 3 statements all have the same conditional on them if education is less than 12. And then these 3 statements have the other condition if education is greater than or equal to 12. So the ordering for SAS versus Stata is backwards. The condition comes at the end, and what you want it to do comes at the beginning. But otherwise, it's the same. Education minus 11 to get the first slope, and then education minus 12 to get the last slope. Otherwise, it's zeros or ones. And in R, it's the same idea with some extra pieces. So example 3 is the name of the data set. The new variables to be created is after the dollar signs. So the conditionality in R happens inside this bracket. So the which statement means, hey, if this is true. And you can't just have education minus 11 like the other packages. You have to put the conditionality here as well. So one function to cover the slope from 2 to 11, and then the other function for people who with greater than or equal 12 years of education right there. All right, how are we doing? Any of that you want to hear again or ask about? Making new variables? So our 4-step process to doing analyses. Step 1 is figure out what variables you need to make. We just did that. Remember what step 2 is? Put them in a model. So step 0 in the sequence is like figure out what the model needs to look like to answer your research question. 1 is make the variables, then 2 is estimate the model. So we can estimate it. So here's my model, my general linear model. So my 3 new predictors go in to the model, predicting income, highlighting them in all the places here. The thing that people screw up when they try to do this for the first time is that folks often want to put original education in here too. It doesn't go here. These 3 new predictors cover the distinct ranges of education that we want separate slopes for. So original education is not in the model. We made the slopes to replace it. If you were to accidentally put in original education in addition to these 3 slopes, one of them would have dots where the estimates are supposed to be because it's redundant. So income is the outcome variable. It goes before the equals. Income is the first variable in regress because it's the outcome. And it is the thing before the squiggle tilde in R as the outcome here too. So the name of my analysis in R is being saved as model ed3, meaning 3 slopes for education. So I'm using the ANOVA function to get the residual variance. I am saving the output to another object so that I can get confidence intervals for it. And then the rest of this stuff we'll talk about in just a second. All right. Shall we see what happened? Why not? So here's my model summary table. So first question on your homework, always that number, residual variance. The reason it's always the first question is because if you get this right, I know that you have the right model. Otherwise, that number is the amount of variability. Is it explained or unexplained? Which is it? Unexplained. Yep. This is what's left. Mean square error, meaning I don't know why some people still make more money. I controlled for education. So this is like a number that symbolizes all the reasons that we don't know why there's variability in this outcome. Degrees of freedom are right here, numerator, denominator. Model is numerator, error is denominator. It's 3 because I got 3 slopes. I could have added 730 more. F is my test statistic for the 3 slopes combined. And here's the p-value that goes with the F. If the 3 slopes were 0 in the population, it is highly unlikely we would have seen slopes this discrepant from 0. So the model's significant. How good it is? R square right there. 16% good. So is this 16% explained or unexplained? This is explained. So I'm making a point because these are opposite. Residual variance is the amount of variance unexplained. R square is the proportion of variance that is explained. So ideally, R square should go up, meaning your model has explained variance, and that translates to mean square error going down, less left over.
Does it mean that if you mean, I'm trying to understand how do you make the residual variance for an empty model, like which includes the whole residual.
So it would be the residual variance from an empty model.
Yeah, basically without the reduced residual variance.
Yeah, so it would be that minus what's left divided by where you started. What it was minus what it is over what it was will give you the 16%. So this is a proportion. So the variance used to be 16% higher, would be, I think, another way to think about it. Yep, but it is relative to the empty model as the starting point. So if you have an empty model with no predictors, you necessarily have an R-square of 0. And then it's the change from that point.
So if you add like 16% to 159.6119, if you
Uh,
add like 16% of that number, that would be the
It's
original residual variance.
159 is 16% of the original number, is the way that I would say that. Yep. So then we get to the more specific answers. Intercept, that's my predicted income level for somebody with 11th grade. And I know that because that's how I set it up. 11th grade is when all of the predictors are 0. So that defines my model reference point for what the intercept is going to tell me. So this intercept is 8.53, has a standard error of 1.7. I have a significant t-value about this. Do I care? Make this a little bit bigger. Does the fact that this intercept is statistically significant, does that go in my results section, yes or no? Deborah, shaking your head? You're correct. Why not?
Because isn't F the test statistic?
Well, this is, so T is for testing one thing and F is for testing multiple things. But I was asking about this one thing specifically. So it's okay that it's T, but I'm asking, like, what does a significant intercept tell you?
We're not predicting, so.
It's not a slope, it's an intercept, yeah. So the intercept tells us that people who have an 11th grade education make $8,500 a year. And the null hypothesis this is being tested against is 0. So that, yeah, so it means that $8,500 is not 0. I bet to those people it sort of feels like it, though. That does not go very far. Question?
Does it mean that every intercept will always be significant?
Odds are good, yeah. I can only think of a few situations in which you would care about this. 0 would have to be a meaningful value on your outcome to compare against. So for instance, if you had some kind of like, I've seen thermometers where like 0 is like you don't care about something, and a positive value means that you really like it, and a negative value means you really hate it. Like if you wanted to say that someone's prediction is, you know, different than neutral, like in that case, the intercept would tell you that, but that's the only type of situation. So yeah, this is not helpful. The intercept tells us where the slopes operate from as a starting point. So less than high school, that's the -1, but it is non-significant. So for every additional year of education among people who didn't graduate high school, they are predicted to make $268 less per year of education. It's a negative slope, but non-significant. So that one is functionally not different than 0. So there's no relationship between education and income amongst people who don't have a high school degree. If you get a high school degree, now that one picks up where the first one left off, $4,600 more, which is a positive slope that's significant. And then after 12th grade, for every additional year of education that you have after 12th grade, you make $2,100 more. And that is also a significantly positive slope.
If the intercept is not significant, does it mean that we need to center it
No, if the intercept is not significant, it just means that that predicted outcome is not different than 0. But I mean, you could center it at a different place. It doesn't matter. Okay. So let's say that I write up these results and I submit it to the Journal of Obvious Stuff. And reviewer 2 comes back and says, I don't think you need this fancy smancy linear spline model. I think this looks like you can fit this with one slope. How do I respond? Any ideas? How could I justify the need for separate slopes?
The fact that the slope is so irregular, you wouldn't catch like a true statement of if you were to just generalize it with just one slope.
Yeah, if I were to generalize it by one slope, the question is, am I missing something, right? This person thinks that I only need one slope. So how do I answer to justify my 3? It was insignificant, and then it was significant. Things changed in the splines. Ah, yes, but this slope is not different than 0. The other two are. But what we don't yet know from these results is whether or not we could collapse and estimate one slope instead. What we don't have yet is a test of whether these slopes differ from each other. Because if they don't differ from each other, then putting 3 slopes in would be functionally not different than putting 1 in. One slope cannot explain the less than high school part. Yeah, I would agree with that. But the formal test of whether or not we actually need separate slopes is to test whether they're different from each other. Could you compare the r-square to one with a single slope? Yes, I could do that too. That would be another idea. So I could start with a model that has just a linear slope, one slope, look at the r-square, estimate this model, and talk about how the r-squares are different. But I wouldn't have a significance test that way. It would just be sort of a heuristic approach. So yeah, we can actually test whether the slopes are different from each other in this model. And believe it or not, you already know how to do this. It's the exact same procedures and logic by which we got differences among the non-reference groups for a categorical predictor. One slope minus the other. Here's the output for that, and I'll show you how we did it in just a second. So here's one difference. 4.95 is how much more positive the slope for the change from 11 to 12 is than the slope previous to that. So this slope of negative 0.27 differs from this slope of 4.6 by 4.95. And that difference is significant. So what that's telling me is that these two numbers are not the same. The less than high school slope is not different than 0, whereas the grad high school slope is different than 0. But these two numbers do not tell me directly whether they're different from each other. I needed to do a linear combination of subtracting one versus the other and to compute a standard error for that. And so that's what this additional piece of output I'll show you how to get is telling me. So these two are not the same. What about these two? Here's the test of their comparison. the slope after high school degree is less positive by 2.5, and lo and behold, they're not different. So this p-value indicates that those two slopes are statistically equivalent. So 4.68 is not different than 2.12. So reviewer 2 might have a point. However, this slope doesn't do a very good job of describing what happens after 12th grade anyway. So the model needs some help before I would be willing to collapse into fewer slopes. But if you find that the slopes are different from each other, what that tells you is that one slope would not have been sufficient. That there is a gain to be had by splitting them. So that's what the rest of the code does that I skipped over. These estimate statements in SAS, the LINCOM statements in Stata, and these GLHT commands in R. So functionally what these are doing is saying beta 2 minus beta 1 is the first one. And the second one is beta 3 minus beta 2. So again, the words in these commands refer to what their betas are going to become. The numbers are the multipliers for what you want to do with them. So in SAS, we don't have addition or subtraction signs. It's subtraction because I gave it a negative value. Otherwise, they'd be added together. It's more explicit what's happening in the LINCOM statements for Stata. And in R, you have to tell it what to do with each of the fixed effects in the model. So anything that is set to 0 in these commands mean leave it alone. Don't include it. So both of these lines start with a 0 because that refers to the fixed intercept. So I'm not doing anything with respect to the fixed intercept. Hang on. This one, that needs to be a 1. I must have messed with this and forgotten to change it back. So that first one gives you beta 2 minus beta 1. The second one gives you beta 3 minus beta 2. So I'll fix this typo and repost the handout so that we have the correct version online. So this should be a 1 right here. This one right here was a 0. That should be a 1. And I'll double check the code too to make sure that the error isn't in there as well, and I'll fix it if it is. So this is step 3. Look at your output and see if there's anything else you want to know and ask for it. So in this case, what I want to know is whether the slopes differ from each other, so I'm asking for it. And then step 4 is effect size. So the effect size part then, what I'm doing is using stored results and making the programs do math on them for me. So in SAS, I have saved this table to a SAS dataset and then added a new column that is partial R, which is a function of the t-value and the denominator degrees of freedom. And so then it's added to the result there. So these are correlations. They are effect sizes for the unique contribution of that slope to the model. Here is another way to do the same thing using proc core, but you have to do it separately for each potential correlation. In Stata, you can access stored results after each LINCOM. So if you wanted to use this code, for instance, in your homework, all you have to do is copy this line exactly as it is. It accesses the results that are stored internally to Stata and does the math on them. And the display command means print it so that you can see what happened. The same is true in R, where I have the coefficients from the model as part of the model object that was saved. And then I use that to compute R. So there's the same formula. And you can also use p-core test as a function to get partial correlations as well. And here's the partial correlation command in Stata as well. So that's step 4, get effect sizes. And then step 5, write it up. So words, as usual, for how I would talk about this stuff. Okay. How are we doing? So. That's fair. I appreciate honesty. So just trying to help you build your toolbox as to how to phrase predictor variables to answer different kinds of questions. So something like this would be useful for quantitative predictors that are likely to have nonlinear effects, where you have discrete ranges that have meaning to them, such as this. So let me foreshadow what is coming next time. It is often the case that education is collected in categories, right? You check a box that says, do you have a high school degree? Do you have a bachelor's degree? Do you have a master's degree? And I have seen people take those numbers and treat them like numbers and put a line through them. Whether or not that is acceptable is a testable hypothesis, because a linear slope, another way to look at that, would be as a series of piecewise slopes. And you could see whether or not each one differs from each other, such that a single line would not help. So that's the last example that I have, is answering the question, can I take this ordinal variable and pretend like it's interval? Because that's an empirical question, given the data. So that's what we'll do next time. All right, any questions before we call it a day? Okay, then as I mentioned at the start of class, on Thursday, I am getting kicked out of our classroom again. So we are meeting only on Zoom so that people can take comprehensive exams in here. Yay! Said no one ever about comprehensive exams. So I will be streaming from my basement as usual on Thursday. Office hours start shortly. Let me know if you need anything. Homework's due next week. And it's garbage day. I put it out myself because my husband's out of town. See, I'm multi-talented. I can put out my own garbage, which means I say thanks for coming. See you Thursday. Bye, folks.